We have another example on the board. Please notice that we have to redraw the circuit first. This is the very first thing which you're supposed to do in order to see what's going on in the circuit. Okay, you can do this mentally, but it's much easier to redraw. So I have DC power supply connected to my circuit, okay, and because I have invisible positive sign over here, so my positive terminal has to go right to this point and the negative has to go to the ground. I can erase it, and I have a voltage source which has 15 volts. Next, you're supposed to check in which direction the current is going to flow. Because we use conventional current flow, okay, so theoretically current is supposed to flow from positive terminal to negative, okay? So this is my current, I total. Next, I'm supposed to check at my diodes, right? We have to look at the diodes, and please notice that both of them are going to go in the same direction. I'm supposed to say the arrowheads are pointed in the same direction like my total current, right? So someone is going to say, oh, both of them are going to forward bias, right? No, because one of them is silicon and one of them is germanium. You're supposed to realize that the transition voltage for germanium diode is 0.3 volts and for silicon is 0.7 volts. You're supposed to realize that electric current is very lazy guy and is going to always choose the easiest way to reach the ground. So it's much easier to jump over, I'm supposed to say, past the diode, right, which has the transition voltage 0.3 volts. We can say jump over 0.3 volts than jump over 0.7 volts. Okay, of course the current is not jumping, this is just the expression. So current is not going to even look at this diode. It's not going to bother to go over 0.7 volts if there is much easier way to reach the ground. So current is going to ignore this diode. So this diode is going to behave like an open circuit. This diode is going to be never in the on state. Okay, so please notice that we obtain series circuit, right? So this is the series circuit, and current is flowing right in this direction. So anytime it's current going to the component, you're supposed to label that terminal by positive sign. Anytime it's leaving, you're supposed to label by negative, and because I have resistor over here, I'm supposed to also write positive and negative sign over here. Now, because we can reach the ground, right, from V out without touching any resistor. I mean, if you are going to go counterclockwise to the ground, right, you are not going to have any resistor on the path, right? So we can find output voltage in a very easy way by simply write the KVL equation. So V out is equal negative voltage across the germanium diode, okay, across the diode. So I have negative VGE, and I have plus voltage source. So I have negative 0.3 volts plus 15 volts. So V out is equal 14.7 volts. Okay, so this is my output voltage. Please notice that output voltage is between output terminal and ground. This ground and output terminal, this ground. This ground terminal, right, it's the same. Okay, so anytime you see ground over here and ground over here, means they're connected together. So V out is also equal to the voltage across the resistor. So I can say that V out is equal VR, and this is equal 14.7 volts. Now, if I have voltage across the resistor, I can find the current, right, which goes through the resistor. So I can say that IR is equal to I total. This is also equal to IG, right, E. I mean, the current which goes through the resistor is equal to the total current, because this is series circuit, and this is also the current which goes through the diode. And of course, I'm going to use Ohm's law. So this is equal VR over R, which is equal 14.7 volts over 2.2 kiloohms. So I can say that IGE is equal, because I'm looking for IGE, is equal also to IR, because I'm looking for IR, is equal 6.68 milliamps. Okay, so this is the current in my circuit. Next, I'm supposed to find the current which goes through the silicon diode. Please notice that we said that silicon diode is going to be in the off state, so it's not going to conduct, it's going to behave like an open circuit. So in open circuit, current is equal 0. So I have ISI is equal 0 amps. There is no current flowing through this diode, okay, because current is not going to see it. So we found the currents, we found the output voltage. Now it's time to find the power, right? So power at the silicon diode, I'm supposed to say this is the maximum forward power dissipation, is equal I silicon times the transition voltage of the silicon diode. So we found that the current through the silicon diode is equal 0 amps, and VSI is equal 0.7 volts. This is equal 0 watts, because 0 times anything will give me 0. Next, we're supposed to find the power at the germanium diode. Okay, so this is P GE is equal IGE times VGE, which is equal 6.68 milliamps times 0.3 volts. This is equal 2 milliwatts. Okay, this is the maximum forward power dissipation at the germanium diode. Next, we're supposed to find the power at the resistor. So I have PR is equal IR raised to the second power times the resistance, which is equal 6.68 milliamps raised to the second power times the resistance, 2.2 kiloohms. This is equal 98.16 milliwatts. Okay, so this is the power, right, at the resistor. Next, we're supposed to find the total power. P total is equal the sum of the powers in the circuit. So I can say that P GE plus PR, and this is also equal, I can say approximately, I total times voltage source. So I can say P total is equal, I total we found is equal 6.68 milliamps, 6.68 milliamps times 15 volts. So P total is equal 100.2 milliwatts. Okay, so this is my total power. Total power you can get in two ways: by adding the powers in the circuit or by multiplying the total current by the voltage source. Your answer is supposed to be the same or just a little bit different, but the difference has to be very small. So I got 100.2 watts. So I can say that the problem is solved.